So guys, welcome to the presentation. We're going to take a quick look at the new OM1 from Olympus. And the obvious question is, how did they achieve 2 stops better noise performance and 1 stop improved dynamic range? I did an interesting exercise, and I encourage you to repeat that. I had a look at the Sony official website, and in particular studied the A7 II versus the A7 III. And as you know, the A7 II is a CMOS sensor, and the A7 III a BSI sensor, and both are 24 megapixel. So it's a very similar situation like we see with the EM1 range versus the new OM1. And on the Olympus or on the Sony website, they give a good or interesting explanation for how they improved the noise performance with up to 1.5 EV and the dynamic range with 1 stop. You can see a similar thing on the Fuji website, where the previous camera was the X-T2, a CMOS sensor, and the new X-T3 uses a BSI 26 megapixel sensor. And again, it's very interesting to read how Fuji achieved better image quality, improved noise performance, and dynamic range for the X-T3, and then obviously later the X-T4. So it's a very interesting thing I did, and I like to encourage photographers to do the same thing in the future. The challenge we have with camera reviews is there's a lot of marketing at play, and it's sometimes really difficult to get a neutral opinion of what the camera can really do. So study different manufacturer websites, go to sensor manufacturer websites, look for papers, technical papers, and you will find some really interesting information on the evolution of the image sensor and how cameras are improving today. So yeah, obviously, in addition to what I already said about the Sony, the Olympus, and the Fuji improvements, you would see each one of them refers to the sensor. So the focus is really on the sensor, and this is where most of the improvements takes place. It's important when you look at the sensor to focus in the right area. So the question is, should we focus on the size of the sensor, which in terms of micro four thirds haven't changed over the past years? So the physical size of the sensor basically stayed the same. But when we take a closer look, then we see that the sensor really consists of pixels. So this surface area here, with Olympus at the moment, we have 20 million pixels fitted into this area here, and we really need to go down to pixel level to see the improvements that these sensor manufacturers are achieving. So the first thing they would typically do is improve or increase the resolution of the sensor. The second aspect is speed that they would develop. And the final one is sensitivity, and we're obviously going to focus a little on sensitivity in this presentation, because that is where most of the improvements, image quality improvements, is taking place. So here you see a pixel, a little bit more detail about the pixel. This is a traditional CMOS pixel. And if we look from top to bottom, you see there's a micro lens. So the image signal will be coming from this direction. And you can see it like this. It will pass through the color filter, any other filters that might still be used in cameras. This here is the wiring for controlling the pixel. Then you have a light sensitive surface and the photodiode. This is where the conversion from photons to electrons takes place. So looking at the title, you can see that we're going to have a quick look at the CMOS sensor here. And we're going to have a closer look at the differences between a live MOS from Micro Four Thirds and the CMOS sensor. It's obviously both are CMOS sensors, but Micro Four Thirds is using a live MOS variation of the CMOS sensor. So how can we improve the pixel? There are two dominant ways to improve the pixel in terms of its sensitivity. The one area is the optical efficiency. That's basically from the point that the image signal is coming into the pixel. So it's going through the micro lens, any filters like in the color filter in this case, through the wiring onto the light sensitive area here. This area here is the optical efficiency. Once the image signal reaches this area here, it goes into the photodiode, and here the conversion from photons to electrons will take place. This area we call quantum efficiency, and there's a huge amount of research and development going into improving the quantum efficiency as well as the optical efficiency of your pixel or the sensor. And at the end of the day, these two efficiencies increase or improve sensor sensitivity. So if I take a closer look at the wiring here, this is an obvious problem, because as my image signal enters the pixel, it can be blocked by the wiring, for example, and you will have something happening like this. So the image signal will be reflected back, and this is basically, let's call it image signal chaos, which results in noise, poor image quality, all sorts of problems. So we want to do something about the wiring to improve the optical efficiency of the sensor. If I look at the pixel from the top, from this view here, then you see the wiring, you see the pixel area here. This is the total pixel area. You see the wiring inside the pixel and the opening for the image signal to pass through. Now if just a quick look, and you can immediately see my total pixel area was this, or is this. By adding the wiring here, I basically reduced the pixel area to only this here. So by having the pixel wiring in between the micro lens and the photodiode area here, I'm basically reducing my optical efficiency, or the area I have available to read the image signal. So this is what Olympus also saw, and I guess having a smaller sensor, they were looking for ways to improve the area, the pixel area, and they made it quite a interesting decision by grouping 4 pixels at a time. They shared the wiring with the 4 pixels at a time. So by doing that, they could increase the pixel area significantly, and therefore the quantum, or not the optical efficiency of the sensor or the pixel, and therefore the sensitivity of the sensor. Okay. So let's have a look at an old style CMOS sensor versus a BSI sensor. What happened to the BSI version? And it's actually quite interesting, or simple. They basically took the wiring, removed it from this area, and placed it below the photodiode. Now there are more technical explanations for this, but this is basically what happened. We now removed the wiring here and significantly improved the optical efficiency here. And you can see it by this image here. So in the past, before the CMOS days, we had CCD sensors. They had no wiring like the CMOS, so you had the total pixel area available. Then the CMOS sensor came with a much reduced area, and then the Micro Four Thirds, which improved on the CMOS, the old style CMOS configuration. And today we have a BSI sensor with no wiring, and we're back to the CCD efficiency. Okay, so here you look typically at 50% plus improvement in efficiencies. So what is the difference to a stacked BSI, and what is the benefits of having a quad buyer configuration? So again, we do have the benefit of the BSI configuration. No wiring here in this area here, so I have optimum optical efficiency. It's no surprise, or I would not be surprised, if there's been a lot of improvement in the quantum efficiency, in other words the efficiency or the effectiveness that the sensor can capture a photon and convert it into an electron. Then the wiring has been improved to a new format, and it's basically now called a stacked or a layer format. So we have different stacks, and all they did with the stacked configuration is they put similar features or functions in the same layer. So this might only be computational. This one is probably all controlling the pixel, and the third one here could be speed or autofocus, which is now linked to the quad buyer configuration. And then looking at the quad buyer, as I said, the main advantage for the OM1 at the moment is autofocus, and especially autofocus speed. If you want to know more about the quad buyer configuration and what are the benefits, go and study mobile phones, because this is where we've first seen the quad buyer configuration implemented. And the main benefits those guys had with the mobile phones is incredibly improved autofocus performance on these mobile phones Computational photography also benefited because I have 4 pixels, separate pixels for each 1 pixel. So this would be 1 of the 20 megapixels, but I effectively have 4 smaller pixels for each 1 pixel. The moment I have more than 1, pixel, like in this case 4, I can start doing many different types of computational photography inside the sensor. And there are many benefits and variations that can be done. It's worth a read. Go and do a search on mobile phones. Then what OMDS also looked for, like I said, is the stacked configuration here. And then finally we see that from the documentation that there's a lot of software improvements that happened here also. So one of the things, for example, that they would do with software, they would replace wired functions with software. And at the end of the day, you're addressing speed, the 3 things: speed, sensitivity, which is optical and quantum efficiencies, and resolution. Now the resolution did not increase on the OM1, and I'll show you an interesting example right at the end of the presentation. So what we see is that OM Digital did everything possible to give us one of the most updated type sensors today for the OM1, and it's also a future sensor, so it's not going to be at the end of life cycle within the next 6 or 12 months. I guess the sensor would be able to be good for the next 3 to 4 years as a minimum. So in summary, we see that there's been optical efficiency improvements with the BSI and quad buyer configuration. You would see that OMDS also mentioned a live MOS configuration in this new sensor. I'm not exactly sure how it would function or what the benefits would be, for the simple reason we already removed the wiring here. I can only imagine there are some live MOS benefits in terms of the control here, and because we already have 4 pixels combined at a time, I guess that is taking place there. So there's been a lot of improvement there. They also improved the quantum efficiency of the pixel, the stacked configuration for speed and processing, the quad buyer for autofocus, AI, as well as speed, and then obviously firmware, which again is AI that we see, and some old wired features or functions now replaced by software functions. And this, guys, is basically how they achieved the 2 stops improved noise performance and the 1 stop additional dynamic range. Now, it could be that the 2 stops noise performance is not only these, or let's call it these improvements here. When I compare the Sony discussion with the A7 II and the A7 III, Sony mentions 1.5 here. So let's assume this sensor is better than the BSI sensor used on the A7 III with the stacked format as well as the quad buyer format. But let's assume we did achieve the same noise improvements as what Sony did with the A7 III, so we're sitting here at 1.5 EV. noise performance improvement only by doing this here. Okay, so my final thoughts. This is another way of looking at the image sensor, and I believe it's a very helpful graph, this. So most of the information I present on my website or in presentations like this is a carefully selected information that I present to you. There's so much information, and we can spend hours and days and months talking about sensors. But picking and taking the right information that can help you improve your photography, I think that is one of the most important services we can give to photographers today. So this graph is quite helpful and quite powerful. So here at the x-axis we're looking at photons, and here on the y-axis we look at electrons, and we are interested to see the ratio or the relationship between photons and the conversion of photons and the conversion to electrons. Okay, it's obviously a linear process that you see happening here. So for every so many photons, I will have so many electrons. For a little bit more photons, I will have a little bit more electrons. What is interesting here is each image sensor has a noise floor. So even if there's no image signal onto the sensor, I will have this noise level inside the sensor. And I first have to expose my pixel or my sensor up to this point here before I will see an image signal on the output. Then I have a short noise component. You guys know what sort of short noise is. And each sensor has a saturation capacity, the maximum to which I can saturate or expose the sensor. And then you see here's a signal to noise ratio that I can read from here. So if I have a high signal, clean signal to noise ratio, I will see very little noise in my image. If I have a low intensity signal, I will have a lower signal to noise ratio, and I will have more visible noise. At the same time, I can see the dynamic range for the sensor here. This here would typically be the shadows, the mid-range, and the higher dynamic range areas. And on the right side, you can see the improved image sensor. So let's assume this is something like an EM1, and this is now the OM1. And by doing the improvements which we summarized on the previous page, they reduced the noise floor in the sensor, and immediately the dynamic range increases, you can see here, as well as the noise of the clean signal to noise ratio. So just by looking at these two graphs, you can immediately see, by doing the improvements on the pixel that we've discussed, we can immediately start identifying these two benefits: dynamic range and improved noise performance and less visible noise. This is also an interesting way of looking at it. On the left, there's a summary of what can we expect to see from the new sensor or the new camera. And on the right hand side, you see a very simple explanation of what happens inside the camera. So on the right here, you have your image processor, and this is the image signal that the image processor needs. So this is my 18% gray or my native ISO. This is the compatibility level for an image signal that needs to go into the image processor. So an old school CMOS sensor will typically have a native image signal size like this, with a noise component like this, That means the factory will measure this, and they then need to do a once of gain of this much to get this image signal at that level there. If I improve the image signal like we discussed, the first benefit is a smaller noise floor, a much better signal to noise ratio, and also at the factory I only have to give a small gain, once of gain, to get this sensor on that level there. So let's assume the two sensors are now all at the same level operating. Now if the photographer goes up the ISO with one stop, 1 EV, then we can quickly see what will happen. So we will have a new signal here, but also an increased noise level, because when I amplify this, I also amplify the noise. So when I up the ISO with one stop, I'm amplifying not this noise, but a bigger noise signal now. If I amplify with another stop, I double the noise and one more time. If you look at the new OM1, you can see that this impact of the noise is much smaller. Even with the gain, the once of gain adjustment here, the noise is still very low. And you can see the effect when you start upping the ISO. This will be much smaller or less visible than this one here. So guys, here's the final slide. What we have here is the three areas: speed, resolution, sensitivity, and I added software improvements. These are the four areas, what the improvements we had: lower noise floor, improved noise performance, improved dynamic range, more detail that I can record, and the ability to improve the image quality of the camera. So we can expect all these quite comfortably with the new sensor. And then one final thing, which I don't know if everybody saw, but OMDS did mention in one of their presentations or in some of the presentation material, where they say the final 2 EV ISO or noise improvement is in the handheld high-res mode. So it's obviously a stacked exercise configuration of the image. So like I said, probably with the pixel improvements we have 1.5 EV improvement, and the final 0.5 EV happens then in the high-res mode. So in total we then can expect to see a 2 EV improvement in noise, and that is also probably before any IA or AI noise reduction. So what is the final thing we see with the new sensor? This is really interesting, guys. So typically they would improve the pixel like we discussed here. OMDS kept the megapixels the same. In other words, we see all the benefits that was made or achieved on the image sensor in better image quality. Many of the manufacturers would take these benefits but then add more megapixels to the sensor. So all you do is you're leveling out this again, because if you only increase the megapixels, you would have had a worse image quality and more noise, because effectively the pixel area, the pixel size reduce, and you will see the negative from that. But what OMDS did was they improved, they gave us all the improvements that was done on the image sensor. And this is probably one of the biggest reasons we can expect to see significant improvements in image quality on the OM1. A very logical conclusion. There's one more thing that's quite interesting when we look at that. I can only imagine that OMDS is quite comfortable with a high-res mode and the future of high-res photography, and that it will improve significantly in the future. So I really want to encourage Micro Four Thirds photographers to work with the high-res mode, use it, exercise with it, get used to it. It's a wonderful function. You know, people like to show the fact that we cannot take pictures of flags waving or people running back and forth in a scene, but it's such a small sample of photography. These two examples, there are so many examples where we can see the benefits of high-res mode, and especially the handheld high-res mode. So I really want to encourage photographers to experiment and work with it, because as I said, I can imagine that would be the future. So thank you for listening, and I will appreciate your feedback. Thank you.